Let me introduce to you few concepts related to photochemistry. Most of you must be familiar with the term photochemistry. It deals with the chemical changes happening when molecules are exposed to light. Or we can even say that it is that branch of chemistry which studies the chemical effects induced by light radiation, particularly the electromagnetic radiation which falls in the UV visible region with nanometer wavelength range of 200 nanometer to 800 nanometer. Now, photochemistry deals with the phenomena of both absorption of light and emission of light. That is, absorption and emission of radiations which falls in this wavelength region 200 nanometer to 800 nanometer. Photochemistry deals with, or you can say that we can divide photochemistry into two parts. One is the photochemical processes and the other one is the photophysical process. In photochemical process, we concentrate more on the chemical reactions which happen to molecules when they are exposed to light. See, for example, in this example which I have taken, the molecules A and B, when they come in contact with light, gets transformed to product B. There is a chemical change of both A and B. So there is a chemical change happening to the molecules. So such processes wherein chemical changes happen in the presence of light are called photochemical process. Examples: photosynthesis. You have the ozone depletion, which we had already discussed when we were discussing about pollution, or the natural ozone depletion, wherein the chlorine free radical reacts with ozone molecule to form oxygen molecule and ClO free radical, and where the chlorine free radical is formed when chlorofluorocarbon comes in contact with light, H nu. And photosynthesis, carbohydrates are synthesized by plants using carbon dioxide and water in the presence of light. Light is important there. If light is absent, that reaction will not happen. So when there is a chemical change, chemical process happening in the presence of light, we call it as photochemical process. In photophysical process, the molecule absorbs, the chemical molecule compound absorbs light and goes to an excited state and then comes back to the ground state, releasing some amount of energy. So there is no chemical change happening to the molecule which absorbs light or which interacts with light. There is no chemical change. The molecule goes to an excited electronic state and then comes down to the ground state. During this, for excitation, it absorbs light, and for coming down to ground state, while coming down to ground state, it emits energy or radiation. Now, fluorescence, phosphorescence, etc. are examples for photophysical process. We shall be discussing this in detail later on. Now, let us see what are the difference between photochemical reaction and thermal reaction. Now, those reactions which, the normal usual reactions which do not take place in the, which doesn't need any light radiation, is called thermal reaction. Majority of the reactions fall under this category, thermal reaction. What are the major differences between a photochemical reaction and thermal reaction? Photochemical reaction involves absorption of light or emission of light. Again, happens only in the presence of light. Light is essential, but thermal reaction, light is not necessary. It will happen even in the dark, and heat is evolved or absorbed during thermal reaction. That is, you have this reaction called endothermic process and exothermic process. In endothermic process, heat is absorbed, and in exothermic process, heat is evolved or emitted. But in photochemical reaction, it's not necessary that heat may be absorbed or emitted. Light is definitely absorbed, and presence of light is very much essential. In thermal reaction, temperature has a significant role in the rate of the reaction. Temperature plays an important role, but in photochemical reaction, it is not the temperature which decides the rate of reaction. In fact, it is the light radiation which decides the rate of reaction. A photochemical reaction is selective, involves selective activation. While thermal reaction, the activation is not selective. What do we mean by selective activation or non-selective activation? So in thermal reaction, we know that when you give temperature, supply temperature, reactions speed up. So when you heat the molecule or when you apply temperature, all the molecules in the compound gets activated. They are sensitized or they are activated, and they start, collision happens and all those things. And then the chemical reaction happens. But in photochemical reaction, it's not necessary that all the reacting molecules must be activated or will be activated. Okay, and even if a single molecule gets activated, it's not necessary that the whole molecule has to be activated. In photochemical reaction, the molecules which are sensitive towards light are activated. The functional group which are sensitive towards light radiation are activated. So that's selective activation. Say for example, in the ozone depletion we had mentioned earlier, I said CFC molecule gets converted to chlorine-free radical, or chlorine-free radical is formed from CFC when CFC is exposed to light. And this chlorine-free radical reacts with ozone. Ozone is not activated in the presence of light. So it is the CFC which is being activated. So you take CFC, you take ozone in a reaction pot, induce radiation, light radiation, expose this to light radiation, only the CFC gets activated. Okay, later on ozone reacts with the product of light activation. So photochemical reaction is selective in activation. In thermal reaction, the Gibbs free energy is negative, while in photochemical reaction, it may be negative or positive. Now, when the molecule is exposed to light, or when the compound is exposed to light, the light may be reflected or transmitted or refracted or absorbed. In photochemistry, we are more concerned with this particular phenomenon, absorption. When light is induced or when the molecule is irradiated with light, what happens when the molecule absorbs light? What are the changes which happen when the molecule absorbs light? Now, the major change is that the molecule gets excited to an electronically excited state. The molecule absorbs light and goes to an electronically excited state. The phenomena of absorption can be explained based on photophysical laws or laws of light absorption. There are three photophysical laws, namely Lamberts law, Bayes law, and Beer-Lambert law. It is these three laws which can be used to explain the absorption of light by molecules. Let us see each law individually. Let us first take up Lambert's law. Now, Lambert's law states that when a beam of monochromatic radiation passes through a homogeneous medium of a particular thickness, The rate of decrease of intensity of the radiation with the thickness of the absorbing medium is directly proportional to the intensity of the incident radiation. That is, when you have a medium with a particular thickness, when the light is incident on the medium or on the material, the incident line passes through the material and some amount of light is transmitted out. So meanwhile, what happens? Some amount of light will be absorbed. It is the rest which is being transmitted. So the difference between the transmitted light and the incident light, that is the rate of decrease of intensity of the radiation, depends upon the or is directly proportional on the intensity of the incident radiation. In other words, Lambert law gives us an idea about absorbance and the intensity of incident radiation. How much light is absorbed by the molecule depends upon the intensity of the incident radiation. So you can put it as minus di by dx is proportional to I. I is the intensity of incident radiation. You can take off the proportionality sign and you will get minus di by dx is equal to k prime I, where k prime is the absorption coefficient, which depends on the nature of the medium and the nature of the radiation. So Lambert law is a really linear relation between absorbance and incident radiation, or absorbance and intensity of incident radiation. Now coming to the next one, the Beer's law. The Beer's law is also similar to the Lambert law. If Lambert law describes the relation between the decrease in intensity with the intensity of the incident radiation, here the absorption is related to the molar concentration of the solution. So when a beam of monochromatic light passes through a solution containing an absorbing substance, the rate of decrease of intensity of the radiation with thickness of the absorbing medium is directly proportional to the molar concentration of the solution. What is the concentration of the solution? Depending upon that, there will be a decrease in the intensity of the radiation. Quite obvious, because depending upon the concentration, the absorption changes. And it's the only what is left after absorption which is being brought out. So in other words, absorbance is directly proportional to the concentration of the solution through which the light travels. So here you can put it as minus di by dx is proportional to C. In Lambert's law, we had put it as minus di by dx is proportional to I. Remove the proportionality constant, you get k double prime C, where k double prime is again the absorption coefficient, which depends on the nature of the medium and nature of the radiation. So Beer's law is a direct relation between absorbance and concentration of the solution. Now next is the Beer-Lambert's law. The Beer-Lambert law is a combination of Beer law and Lambert law. If Lambert law gives us the relation between absorbance and intensity of radiation, Beer law gives us the relation between incident radiation and concentration of the solution. Beer-Lambert law is a combination of these two. That is, Beer-Lambert's law says that the rate of decrease in intensity is proportional to the intensity of the light and the molar concentration of the solution, or absorbance is proportional to the intensity of incident light and molar concentration of the solution. So when you have a medium of x thickness, incident light passes through it and some amount of light is coming out, and the difference between IO and IT, or the rate decrease in the intensity of radiation, is proportional to both the intensity of the incident light and the concentration, that is IC. You remove the proportionality constant, you introduce the term K, where K again is the absorption coefficient. Okay, so this is the Beer-Lambert law, combination of Beer law and Lambert law. And Beer-Lambert law gives us an idea about, or gives us the relation between absorbance and intensity of incident light and the concentration of the solution through which the light passes. Now let us come to or take up the mathematical expression for Beer-Lambert law. We'll start the derivation of mathematical expression of Beer-Lambert law using this equation. Minus di by dx is equal to KIC. So let us put that as equation number 1. Minus di by dx is equal to KIC. Now you just rearrange this. You put I to the denominator on the left hand side. You get di by I is equal to minus kc dx. You take dx to the right hand side and also the negative charge. Put it as equation 2. Now integrating to bring it to the whole solution, you integrate it from I0 to I and the right hand side from 0 to x. Okay, on integration, what you get is ln Ix by I0 equal to minus Kcx, where x is the thickness, C is the concentration, K is the absorption coefficient. I0 is the intensity of the incident light, Ix is the intensity of the light which comes out after passing through a distance x. Taking log, you get log Ix by I0 equal to minus K by 2.303 Cx. Put it as equation 5. Now minus K 2.303, if you want to remove the negative sign over here, take the reciprocal of left hand side, you get log I0 by Ix is equal to K by 2.303 Cx. Now K by 2.303 is a constant and can be put as epsilon. K by 2.303 is epsilon, so the equation changes to log I0 by Ix is equal to epsilon Cx. Now what is epsilon? Epsilon is called the molar absorption coefficient or molar extinction coefficient. Epsilon is nothing but K by 2.303. Now this equation number 7 can be rewritten as A equal to epsilon Cx, where A is called the absorbance or optical density of the solution. Okay, you are rewriting equation 7 as A equal to epsilon Cx. A is the absorbance or optical density of the solution, and it is nothing but log I0 by Ix. We have put instead of this I0 by Ix as A. And the ratio of Ix by I0, that is transmitted light to the intensity of the incident light, is called transmittance. So you can put A equal to minus log T. This one here, you can change it as minus T. So you get A is equal to minus log T. Okay, so try to remember the equation number 8 and also this final equation, A is equal to minus log T. Now we need to define what is epsilon, the molar absorption coefficient. We shall take up equation 8 and then go for the definition for epsilon. Now equation 8 is A is equal to epsilon Cx. Now when this epsilon can be rewritten as 1 by Cx log I0 by Ix. Okay, you rearrange this and instead of A, put log I0 by I0 by Ix. You get this expression, equation number 9. Now when Ix, that is the transmitted radiation intensity, is 1/10 of the incident light, intensity of incident light, and C is 1 molar. So when you take Ix is equal to 1/10 of I0, what you get will be log 10, because I0 divided by 1/10 I0. So I0 and I0 gets cancelled and you will get log 10. Log 10 is nothing but 1. And you are taking C as 1 moles per liter, 1 molar, concentration as 1 molar. Then epsilon will be 1 by X. That is the reciprocal of the thickness. So the absorption coefficient is the reciprocal or molar absorption coefficient is the reciprocal of the thickness. Okay, so epsilon can be defined as the reciprocal of the thickness of 1 molar solution, which reduces the intensity of the radiation by 1/10 of its initial value. That is, Ix is I by 1/10 I0. Now every molecule or every solute has got a characteristic epsilon. Epsilon is characteristic of the solute and it has got the unit liter mole inverse centimeter inverse. Liter mole inverse centimeter inverse. Now coming to the limitations of a Beer-Lambert law. Beer-Lambert law is applicable only if the solution is dilute, if there is no solute solvent interaction, and if the molecular state of the solution does not change with change in concentration. I'm sorry for the spelling here, molecular. Okay, so if these three conditions are applicable or satisfied, then only the Beer-Lambert law holds good. Otherwise, there will be deviation from the Beer-Lambert law. So the solution must be dilute, there must not be an interaction between solute and solvent, and there must not be any change in the molecular state of the solute with concentration. Coming to the application of Beer-Lambert law, you can estimate the concentration of the solute in a solution. The amount of solute in a solution can be estimated using colorimeter or spectrophotometer. So what you do is you take a solution containing this solute with different concentrations, known concentrations, and check their absorbance using colorimeter or spectrophotometer, and plot a graph of absorbance versus concentration. You get a straight line like this. Okay, for different concentrations you plot absorbance, you get a straight line passing through the origin. Now take the absorbance of the unknown solution and then mark it in the y-axis and extrapolate that point towards the graph and then towards the concentration axis. So this particular point will be the concentration of the unknown solution. So this is one of the application of Beer-Lambert law. You will be doing it in the lab later on during the experiment. Okay, so this is few things related to photochemistry. In detail regarding the other concepts of photochemistry, we shall discuss in the next presentation. If you have any clarifications to be done, please feel free to ask me. Thank you.